most of the talks in ITAP, I understood almost everything what that was speaking about, and I appreciate it very much. Talks and and I'll try to do my best to follow this today to precious principle to give clear talks. And then after that, we spent, well, quite a lot of time on the phone talking about market numbers and hyperbolic geometry. And I've tried and especially in particular, that hyperbolic geometry is very simple and it could be used anywhere it contains all mathematics altogether. And just to show that, I want to say that if you go just to the forest, you take a jump and know what's in Churban in Russian. So, and from this Churban, you can very easily to get hyperbolic geometry. So I just want to present you this device. And you can see a horocycle.
Yes, you make it yourself?
Yeah.
Nature did it.
Well, with this, well,
Gladly.
so well, and at that time I was I was very excited about hyperbolic geometry, and well, but my subject of my excitement changed with time, but they include previous also subjects. But today I'll speak about the subject of my excitement now is just Steinberg symbols, and well, they have plenty of names, and I'll say, well, I'll start with the definition of a theorem, and then the rest will be just a consequence of all that thing. So definition that well, what is Steinberg symbol? And sometimes it's called Haim symbol, sometimes it's called well, in French it's symbole modéré, well, symbol. And what's that? It's just you have a ring. R is a ring. And the A is an abelian group. And it's a map from, well, the symbol will be denoted by curly braces, but it has nothing to do with Poisson brackets. So it's just, well, unfortunately, it's canonical notation. So it's a map from well, actually, this curly bracket. It's a map from R cross times R cross to A, and I'll denote all the groups, well, A multiplicatively. So then the map just AB goes to, sorry, AB, A comma B goes to AB with the following properties. First property is that AB, it's actually a bi-multiplicative. So ABC is equal to AB times AC. Second property is that they are AB times BA is equal to 1. It's kind of antisymmetric form, but on multiplicative group instead of additive. And of course, it can be extended to tensor product of R star times R star. So in the third property is that A B is equal to 1 if A plus B equal to 1. So this is the only place where the addition in the ring is used. So all others is just multiplicative group.
You assume in ring to be commutative.
Pardon?
You assume in ring to be commutative.
Ring commutative, yeah. But for me, ring is commutative. Sorry, of course, commutative ring. So this is a, well, I'll add the fourth property, which is actually a consequence of this one. But for if R is a field, but well, in general, it's not. So it's a comma minus a is equal to 1. So this is a symbol. Well, I'll give plenty of examples, but not now. Now this is the definition, then the theorem. And the theorem is the following: that so suppose we have a quiver. So we have a quiver. Unfortunately, I need to spend a little bit more time than I expected because Misha skipped a big part of his talk. But so Q is a quiver. And
So this is definition of K2 has to do with definition of K2.
of course, it's just the space of symbols is K2 essentially, but
If I is
it's just character of K2. So quiver is well, and Q prime is a mutation quiver. So well, I'll perhaps say that. So if you have a quiver, there is a procedure which Misha was. Well, I'm
Sorry for my ignorance. If you have, for instance, 1 plus a symbol, what is that? The ring.
sorry, 1
symbol of 1.
1 plus 1 and a.
it's 1.
1 and a plus b.
Homomorphism from multiplicative group to numbers. If you fix one argument, it's homomorphism. So it means that
And the sum, if you have a plus b with c.
a plus b with c, no, well, you can derive something from this statement, but in general, there is no way to simplify this expression. I will compute some symbols. So what the mutated quiver? So there is a procedure that takes one quiver, and if you have a quiver, for example, I don't know, I'll give an example, and of course I return back to Markov quivers because it's just the subject of discussion. So this is so you have this quiver, which was in Misha's talk. How to mutate a quiver? What you do, you take a vertex, and you add. You change all the arrows which comes to this vertex. So you fix a vertex, then you change the orientation of the arrows coming to this one, and then you do for every pair of arrows entering and leaving, you add another arrow. Well, you have here entering, sorry, yellow, the entering and leaving. So you have 4 arrows in this direction. And then you contract. So you have 2 arrows one direction, 4 in another. So you just obtain the quiver, which looks like that. So fortunately, well, in this particular case, the original quiver is amorphic to the mutated quiver. This is Q, this is Q, and this is Q prime. And what you do, suppose, well, you have the space which is R star to the power of vertices, and you have a map to R star to the power of vertices of Q prime and of Q. And in this particular case, it will be the following rule that if you have the numbers A, B, C here, sorry, maybe here, A, B, and C, and here you have still B and C, and here you have A, here you have C squared plus B squared over A. And in general, the rule is the following, that you take some A K prime, so you take the number associated to this vertex and you change it to the product 1 over AK. You just inverse this variable and then multiply by the product of all the edges from K to L of AL plus the product of all arrows from L to K AL. So this is a rule, standard cluster rule, how you change coordinates and you change the.
But what if numerator is 0? Then you don't land in R star.
Yeah, I don't. Well, it's a birational map, so this is not defined. Yeah, there is some problems with that, but well, sometimes it's possible to avoid them, sometimes not. But this is it's now the theorem. The theorem is the following: that if you take let omega be the following. There's a product over all arrows here. Sorry, all arrows from K to L of AK comma AL times the product over I minus 1 AI. Well, K. Then, well, the theorem is then omega is mutation invariant. So it means that you compute this expression for the Q or Q and Q prime, and you change your variables accordingly, then this expression doesn't change. Yes.
Depending on L?
No. It's product over all possible L's. I fix K. Sorry, I fix K both. And here K is not fixed. Okay, L. It's a product over arrows. Sorry. No, I feel just a product over arrows. I do not fix neither K nor L. Just I take here's the product over arrows, here the product over vertices.
There's the comment about zeros that because of the Laurent property, in fact, the orbit of any sequence of mutations is always defined. Your initial cluster belongs to R star.
No, for positive. Only for
Well, it could be zero.
I mean, as a
It
Laurent
could be
property.
zero.
It can be, but I mean, it's defined as a monomial.
No, I prime can be 0.
No, it can be 0, but it formally it's defined in terms of initial cluster.
Yeah, well, actually, this Laurent
Yeah,
property, I'm convinced that one can use prove the Laurent property using the theorem.
Yeah.
Actually, it's kind of
Yeah.
well, I didn't do that yet, but I'm not sure that well, it's quite possible to do a bug-free proof of Laurent property because without caterpillars and all that. Yeah, but well, it's not yet done. So this is zero. So just I'll do an example in order to show that this is well, actually it's an exercise. So this is a very easy theorem to prove, and I'll try to. You need all 4 properties. You need all 4, yeah, but I'll do it for an example, and for generic cases, just a little bit longer. So example, let's consider the simplest possible river. This is just 1 arrow, not the simplest. Well, so we have A and B, and then you have a mutation in the vertex A, and you get something of this form. So this will be 1 plus B over A and B. And then we can compute the symbol for that. So that will be B 1 plus B over A, which is equal to minus 1 minus B minus 1, 1 plus b over a. Now I can, well, I decompose by multiplicativity. I have b 1 plus b times b a inverse times these two terms minus 1 b times minus 1 1 plus b times minus 1 a inverse because a is in the denominator. So because the symbol of a b inverse is equal to a b inverse. So it's homomorphism group of groups. And then
Well, I mean, formally speaking, you should put inverse of minus 1a, but this is an element of
yeah,
order two.
exactly. And minus 1 a squared is equal to 1 because it's equal to 1a. So it's always minus 1 is just plus minus 1. So this term is actually is just the problem of sign. So it's nothing more. And then you just multiply using the multiplication of this these two. You can multiply them, and you get the minus b 1 plus b. Here you can exchange the 5 factors and get rid of minus 1, so it will be ab. And the remaining facts, it's just minus 1a, b minus 1a. And this is equal to 1 because the sum of these two is equal to 1. So this is equal to 1. And well, and you reproduce, and this product is just the original sample. So everything, it's fine, and you can do that in this exercise. Then you lost in my talk, so you have time. You can, it's enough. Time of the talk is well enough, or just after. So this is a simple computation. Now I'll speak about consequences. Sorry. Before speaking about consequences, I'll speak about examples. And the examples, there are of symbols. In order to speak about something, it will be, well, let's take for the ring, R is just rational numbers. And P is a prime. Sorry, maybe even before that. Let's define the symbol, which I will denote A, B, positive, infinity for some reason. It will be equal to minus 1 if A is negative and B is negative, and 1 otherwise. You can easily verify the property that if your sum of two numbers is 1, then at least one of them should be positive. And the property is always obviously satisfied. The multiplicativity is also quite obvious. So you have that. Another symbol is the following. So let's P is a prime. And let's take here is A is now our abelian group is just plus minus 1. Now P is a prime in abelian group will be Z over PZ. And the formula is the following. You take the product of AB, and this is equal to minus 1 to the power degree PA degree PB, A to the power degree PB divided by B to the power degree PA. This expression, so what is degree of with respect to P? So any number A can be written as a power of p to the power of alpha, where alpha is, well, maybe I should write p to the power of degree p.
It looks like A is Z mod 2 because you have -1 to some power. Why is A Z mod P in this example?
No, because this expression is z mod p.
But
This is plus minus one.
right, but map is take arc cross times arc cross into A. Yes.
Yeah.
But
A is this thing.
but your
Minus one
value,
is always in there. This is
well,
like-
it's one. If P is odd, this is just one, right?
minus
Ah,
one.
Oh,
not necessarily
-1.
zero.
Okay, okay.
Minus one's not necessarily zero.
Okay, -1. Okay, yes, yes.
It's not necessarily one. Sorry. And here is just degree is p to a times r over s, where both r s are prime with p. So it's just the degree how many times you have p in this number, and this pot can be positive or negative. So you compute this expression. Then if you take this ratio is prime with order of that, the degree of that, degree p of this ratio is equal to 0, because the degree of the numerator is the same as the degree of the denominator. So this is a number.
It's a product of these two things. Okay.
It's a product of these two. Sorry. It's not.
I didn't.
It's not a. Yeah, it's a product of these two. And I just put in bracket because to say that this is a. Well, maybe it's easier to compute the symbol. Just yes.
Sorry, I think I'm confused about the same thing that Pasha was, but I didn't understand the answer. So on top you write A is equal to +/-1, and then you write that A is Z mod PZ, but A +/-1 is not Z mod PZ.
No. That's a different example. That's another example.
That's another example.
Two different examples.
Okay.
This will be P.
Okay.
So if you have a scheme, then for every point, there's same symbol. For instance,
I'm sorry, correct. Do you mean your abelian group to be what's written or as a multiplicative?
Multiplicative. Thank you. Well, maybe it's easier to compute actually practical life. It's the following. So if you have the two numbers AB, which are prime, AB and Z, and they are prime with P, so AP is 1, BP is equal to 1, then AB is 1. So if there are two numbers which are prime with P, then the symbol is 1. A P is equal to A, and PP is equal to -1. Well, of course, you can generalize that again with any scheme. So you have, I don't know,
one
a
dimension.
number field, one dimensional. You have prime ideals, etc. So you can do this. So this is an example.
Or functions on a Riemann surface.
Yeah, that I will speak a little bit later about functions on the Riemann surface directly. But now I just simple consequence. So consequence, which was kind of surprising for me. I didn't know about that, but there is a consequence of the following. So let's consider the Teichmüller space TD. And this is Teichmüller TD, so Teichmüller space decorated. Teichmüller space. What's decorated with horocycles, which you can see on this thing. So they're all punctures. So you have essentially, you have a surface, you have punctures. You do not have all holes, you just have punctures, and you have horocycles about the puncture. And the claim, which also you can believe Misha, that this Teichmüller TD is actually isomorphic birational to are positive to the power edges of the graph, edges of a triangulation. And well, I will continue maybe here. And if you change triangulation, then well, the quiver, which corresponds to that which Misha was also explaining, that if you have a triangulation, whatever, you can construct a quiver out of it. Which is just you take vertices at the edges, and every time you have a triangle, you just put an arrow between them. And then, well, these are, well, you have a map from this collection of numbers to Teichmüller decorated Teichmüller space. And the claim is the following, that this, if you have on every edge, you have a parameter, which is a well, a1, a2, etc. Then you can compute omega, which is just a product of the symbols ai, aj. For every arrow between these 2 points, you have a product times the product of -1 a. And this is equal to, well, and this is, and you compute with p, is modular invariant. Sorry. On Teichmüller, you can consider Teichmüller space, but not any point of Teichmüller space, but only points which are which with rational coordinates. So you have Teichmüller space, rational points of Teichmüller space. And for rational points on the Teichmüller space, you can compute an invariant. It's using, you take any chart, compute the invariant, and this number is invariant. So it's actually a function on the modular space, not a Teichmüller space.
So A is the lambda length.
A's are lambda lengths, exactly. Moreover, actually, it's a function not only decorated Teichmüller space, but the Teichmüller space itself. It doesn't depend on the choice of Haro cycle. It's easy to show. So that you have some function on a rational Teichmüller space with values in Z over PZ for any P.
The lambda lengths are rational then.
Lambda lengths are rational. Lambda lengths are rational. Yeah, well, which is kind of was surprising for me that find something modular invariant, and this coordinates is always a surprise. So here you can find something modular invariant, and so therefore the space is split into parts according to, well, according to the value of the symbol for any P.
If you take instead field of rational functions over complex numbers on one variable.
Right.
Then you get a family of Riemann surfaces. And to this family you attach.
Well, it's not really family because well, maybe you can do something like that. Maybe I'll say a few words.
Well, let's say real functions.
You should have real functions and
Positive values on the real line.
perhaps it's I hope that it's possible. Well, I played a lot, but not in all possible ways. It's just I invite you to play this construction. It's really very simple. So example, I come back to Markov numbers. So for example, Markov numbers. What are Markov numbers? And for example, you have well, how you can view from cluster point of view, you have a cluster quiver, which actually corresponds also to Teichmüller space of a torus with one puncture. And you put numbers here, and you put ones here, and you mutate. For example, if you mutate once, you get 1, 1, 2, 2, 1, 1, and etc. You can mutate in all possible ways. and you get plenty of numbers, triples of numbers, and in particular, for
The
example,
triples are this eight. Like,
these are A's. Yeah, these are A's. So in particular, if you make a few mutation, then you get the numbers which are 13. You get, well, I don't know, 13, 34, 100, 25. Well, the first bulk of triple, which is not, well, with the numbers relatively big, and then you can compute the symbol, which is 13, 34 p, 34,325 squared because there are two arrows, then 1,335 25 comma
Minus
comma 13
squared.
squared and times -1 13 45 34 25. And well, and then you can play a little bit and show that actually this is always 1, and the non-trivial piece where it's non-trivially 1 is actually 5, for example. If you take 5, then this relation is non-trivial because well, there are, well, for if you take p equals to, no, 7, it's 1 identical because all terms are 1. But if you have 5, then you can compute that. Just to show that it is not very complicated.
I don't understand because you said it is mutation invariant. So
Yeah.
if I compute it on 111,
It's 1.
right? So
Therefore, this is also 1.
okay, fine.
You can verify that.
Yes, okay. But why did you say that if p is 5, I don't get 1?
Yeah, no, I mean, if you p is 7, all factors are 1.
Trivially
1. It's
Yeah.
trivially 1. And
Okay,
5 is non-trivially 1 because this animal is divisible by 25.
you.
Yeah, that's, well, maybe I'll just leave it in an exercise. So
But this theorem applies to universal symbol. You can simply take K2.
of course, it's
why
applied to universal.
Specialize to something.
Well, for example, I made computation and I want to verify if I made a mistake or not. I compute this animal and then verify. Yeah, this actually helps. So you have some invariant for any p. And for Markov numbers, well, the conjecture is the following. So suppose you have a point, so a point of cluster variety, a point a1, an is integer. Definition. If well, all mutations of this collection is equal to is integer. So all mutations are in z to the power n.
But because of Laurent phenomena, it's enough to check for 1 or
Well, it's obvious if all numbers are equal to 1, then it's obviously integer. But the claim if there are other points which are integer. So if it may happen that you take any sequence of numbers, mutate them and keep them, they are still integer. If for round phenomenon, they are rational because you have denominator. But suppose you have numbers which are always remain integer. Then conjecturally, you can make them equal to 1. So it was my conjecture. It was my conjecture for many years ago, and I proved it for the case where related to Tyche mirror space. And but unfortunately, Sophie Maria Genou gave a counterexample. It's not correct. But now I modify the conjecture.
Can you repeat what's not correct?
Not correct that if you have a collection of numbers such that if you mutate them anytime you want, and you always have integers.
Yeah.
then you can mutate it to,
You mean
One,
it's
one,
in
one, one.
orbit of one, one, one.
yeah, you can make them
Yeah, I
equal to
think
1, 1, 1, 1.
we- Somos 4 gives an example.
Right,
Sophia,
you think, well, maybe,
I
maybe.
mean, I think so, yeah.
But now I modify the conjecture. And
Integer, yeah, but
and I omega equals to 1. So if this invariant is equal to 1, then it's possible, because in this Sophia's example is equal to 2. Well, it's
That's
equal.
how she checked that it was not equivalent to 1, 1, 1.
Uh,
Is it?
I already forgot. No, definitely not, because, well,
Sum of 5, actually, there's 2 orbits on the same course, actually, so.
Somas 5 as well. Yeah, yeah, yeah. Well, Somas is also, of course, is an example of that.
This provides a simple proof that her example is a counter example, right? That you can.
Yeah, certainly, certainly. Yeah, so I forgot when I started. It's, well, how much time do I have? Sorry.
Do you conjecture that this is true if you have two integer elements with the same omega, they are conjugate?
Perhaps not. Perhaps not. It's too hard, because for like mirror space, maybe it's possible even like
Universal omega in K2 of Q.
well, yeah, in K2. So for example, for all primes, yeah, maybe not, maybe it's not. Well, I do not dare to put it this way, of course. So now about functions. So there is one example.
said you wanted to correct the conjecture, sorry.
Yeah,
Yes.
yeah, I want to conject omega equal to 1.
That's the con-
Well,
So if you have something in an integer point, and you can always do that.
any group from any. It's all symmetrical.
It seems to me that in Sophia's proof, it's something geometric. So it was geometrical proof. Not.
Yeah, and if.
Well, another remark that there is another symbol. So example of a symbol is the following. So, well, first I'll start with a construction which apparently has nothing to do with that. So let's take the space X C star cross C star, just a torus. And on this torus, there is a line bundle E over the torus with just a line bundle with a connection form alpha equals to here, if the coordinate here is equal to F and coordinate here is equal to G, then alpha is equal to 1 over 2 pi I d log F, log F, sorry, log F d log G. So of course, this is not a function, well,
This is curvature of the connection.
no, there is no D here, just one
Oh,
form.
G, okay.
It's just log of F, but it's multivariate. But it's not multivariate is not bad, because it means that its connection it's a connection in a non-trivial line bundle. And on C star cross C star, there is a non-trivial line bundle with Chern class 1. And this is not algebraic, because there are no algebraic non-trivial line bundles on Steinberg varieties. So this is the only, well, you can compute it as, well, this space actually, total space E is also can be written as a quotient. You take Heisenberg group over complex numbers, and you can take a quotient over Heisenberg group of integers from upper triangular matrices, 3 by 3 upper triangular matrices with complex numbers divided by upper triangle of integers, you get the quotient. And here you have that invariant form, which is given by, I don't know, you have matrices A1, 1, 1, A, B, C. And you have the form DB minus A, D, C. Sorry. Right. And this is the left invariant. And you can take a quotient, you get right quotient, and you have a connection form on the quotient. So you have a line bundle. And of course, the curvature d alpha is 1 over 2 pi I df d log f d log g, which just a form. So claim, if we take I take this line bundle E and I restrict it to the plane f plus g equals 1, then it's trivial. Well, easy exercise.
What do you mean by?
It's trivial as a line bundle with connection. So it means just a trivial bundle with connection. Now let X be a variety. Well, any algebraic variety, I don't know. We see, for example. And F and G, then let's consider the claim example now. Now example of a symbol. This is variety. Mar R is just regular function of on X. And A is the space of line bundles with connection. It's a group with respect to tensor product. So I can take now F and G is equal to, you take, just consider the map F and G as a map from my variety to C star squared. I take inverse image of E. And I claim that this is a symbol. For obvious reason, because of that. If you restrict to F plus G equals 1, then it is the symbol. So you can construct out of well, two functions, you can construct a line bundle on any variety. You have two functions on the variety. Consequence, we, for example, Teichmüller space T of sigma possesses a canonical line bundle with connection. And of course, it's homomorphic. Well,
Algebraic, yes? Or
not algebraic line bundle. Here it's not actually it's not complexification of Teichmüller space, but this is a bundle with connection. It's rather well.
What's the definition of the bracket?
Pardon?
Symbol. What's the definition of the symbol again?
Symbol.
Just start.
You take two functions. You consider these two functions on a manifold as a map to C star squared. But on C star squared, you have a line bundle with connection. So you can pull back it on your manifold. You take a line bundle with connection. Now, if you have, for example, if you have a symbol, so it means that if you have products of, sorry, maybe I should. So you, for example, if you have a product of symbols, no,
just a second, but when you talked about your group, it is group of isomorphism classes.
isomorphic classes, of course.
So then it is not clear. So your Teichmüller space is just contractible. So Isomorphism class of
Well,
what?
Yeah, this is of course contractible, but well, Teichmüller space is contractible. Let's take complexification. It's actually, well, maybe I should say that instead of Teichmüller space, if I replace my field from real numbers to complex numbers, or real but not positive, then I get a manifold. So the corresponding manifold complexification of Teichmüller space, Teichmüller is just homomorphisms of phi one of my surface to SL2C. And on this space, this space is non-trivial topologically, and you have plenty of line bundles. Non-trivial line bundles here.
It's holomorphic line.
Homomorphic line bundles on this space. Well, quotients by the conjugation. This is there. And if you take the, well, you have this line bundle with connection. If you have instead of connection, you forget about your connection, but remember all about this curvature. You have a symplectic form, or pre-symplectic form. And this symplectic form is actually the starting point of all this story, because if you have, well, we knew that there is a canonical Weil-Petersson symplectic form, which can be expressed in cluster coordinates. So what I'm telling you that the fact that symplectic form is invariant under mutation, under mapping class group action, etc., has a consequence that there are plenty of other objects which are invariant under mutations, and every symbol gives you somehow an element of this object. And perhaps the last thing which is also I would like to mention, well, there are, well, also you may do the following. Let's consider this where is the formula? Yes, let's consider this connection, and then the claim is the following: that what is monodromy? So you have a connection, so you can compute monodromy, and I claim the following: that monodromy of this connection, monodromy of this connection of alpha, this is given by the following formula. So I will compute the F and G, where F and G now are just maps from the circle S1 to, or are quotiented by 2 pi Z to the complex numbers. So you have a map. So you can compute monodromy, and the monodromy is equal to x, well, 1 over 2 pi I. You can compute it yourself just from the definition. The integral from x to x plus 2 pi I, 2 pi, ln f d ln g times g f close g to the x to the power minus degree of f, where degree of f is how many times f goes around 0. And so it's just degree of f is 1 over 2 pi I, the integral of d log f. And this is also a symbol, just because my line bundle is a symbol, so f and g is a symbol. And this symbol can be considered as a cocycle on the space of function on a circle. It's just a group of function on a circle. It's a cocycle, and this cocycle is nothing but the cocycle of Heisenberg group. So you have a group. Well, you have Heisenberg algebra, trivial, well, Lie algebra, degree 1, you have central extension, and you have a group. And then the group, what is the group cocycle? How to write down the group cocycle? Group cocycle is this one. So, for example, all the vertex operators, etc., can be written also in terms of this symbol. So I stop here and just well, my aim to convince you that symbols are nice. Okay, thank you very much.
Okay, just one quick question maybe. I have a very quick question. So this, in regards with your theorem, with your theorem.
Yeah.
uh,
The only one.
Do you, oh, do you have any idea what happens if you consider higher symbols replacing K2 by K3?
No, no, it's a very good question. Of course, I have, well, they have. No, I do not have that, but I would like very much to have, of course. There is something which is given by Goncharov and Shen, and well, it's not so beautiful that it's sort of.
I allowed myself one question, but okay, that's excluded, Pasha one.
Okay, so, she had two, but, oh.
The first one, second one for investment. It's
So-
at the expense of your talk, but.
Yeah. So Steinberg discovered this Steinberg symbol. He wrote down presentation of the general linear group as generated by upper and lower triangular matrices. And he discovered the central extension of GLN over ring R by K2.
Right.
So does your theorem mean that somehow this extension, not only GLN itself, is some sort of cluster variety or?
Yeah, well, if you describe GLN as a cluster of arrays, and you compute this symbol, that is just cocycle. Just a cocycle for GLN for.
So does it mean that somehow you get a cluster structure on this central extension or?
Well, I don't have cluster structure on central extension. I have cluster structure on the group, but the central extension is this symbol.
And it's so
You
it's
need to-
compatible to the cluster structures.
Yeah, exactly. You take cluster structure, you can take product of arrows, and you get of not on the whole group, but on the subgroup. Well, there is a formula for that as well.
Okay, we can refreshments, so did you stay for this discussion? Let's.
У нас есть соответствие, говорит, что это можно записать также связано с